Welcome to Lecture 4.3, Self-adjoint linear operators. At the end of the last lecture, I introduced the notion of a self-adjoint linear map, which generalizes such concepts such as a symmetric and Hermitian matrix. In this lecture, I'm going to go over those ideas and the main theorem of why these things are so nice, which I stated at the very end of last lecture, except I'm going to assume throughout that our vector spaces are of functions. So instead of saying linear map, we usually use the term linear operator. And instead of using v and w for vectors, I'll use f and g for functions, though you can think of them as vectors as well. So let's let v be a vector space with an inner product that we denote with our angle brackets as usual. A linear operator L, a map from v to v, is self-adjoint if this relation holds. If LF.g equals F.LG for all f and g. In other words, if we can freely move the L across the comma in the inner product symbol. So again, I usually say LF.g because that's just easier than saying the inner product of LF with g. Here's the main theorem, which I stated at the end of last lecture. If L is a self-adjoint linear operator, then first of all eigenvalues of L are real, and secondly, eigenfunctions corresponding to distinct eigenvalues are orthogonal. So now we're going to prove this. So let's do the first part first. So why are all eigenvalues real? Well, let's take an eigenvalue and corresponding eigenvector. So let's say that L times f equals lambda times f, and assume that f is non-zero. Otherwise, this is pretty trivial. So we want to prove that lambda is real. Okay, so how do we do that? What does it mean if lambda is real? Well, if lambda is equal to a plus bi, then one way to show that lambda is equal is show that lambda equals lambda bar, because the complex conjugate lambda bar is a minus bi, and if a plus bi equals a minus bi, then that's the same thing as saying lambda is real. Okay, so that's going to be our approach. So now what do we want to do with this? We don't have much to play with. So here's what we're going to do. I'm going to take the inner product of LF and F, I guess LF dot F as I usually say it. Now I'm going to turn the L into a lambda, lambda F dot F, and then I'm going to pull out the lambda, so lambda times F dot F. And since L is self-adjoint, it's a key property here, that is equal to F dot LF. And now I can turn the L into a lambda again, so this L becomes a lambda. So now we have F dot lambda F. And now I can pull the lambda out of the inner product. But remember, lambda might be complex, so I have to write this as lambda bar F dot F. So now what we have is lambda times F dot F. Oh, let me just remind you that F dot F is non-zero, because that's the norm squared of F, and F is non-zero. So we have lambda times some non-zero number equals lambda bar times some non-zero number, and therefore we conclude that lambda equals lambda bar, and that's exactly what it means for lambda to be real. That's the first part. Okay, so here's the second part. Eigenfunctions corresponding to distinct eigenvalues are orthogonal. I'll use blue for this one. So again, we don't have much to work with. Let's suppose we have two different eigenvalues, let's say lambda and mu, and corresponding eigenfunctions, let's call them f and g. So I'm going to say that we have LF equals lambda f as before, and LG equals mu g. And distinct eigenvalues means that lambda and mu are different. And of course, assume that f and g are non-zero. Okay, so now what are we going to do? Well, I'm going to start with this. I'm going to write down LF f dot g, and I'm leaving some space on both sides because I'm going to work both ways. So one thing I can do with this is I can turn the L into a lambda and pull the lambda out. And the other thing I can do with this is I can move the L to the right-hand side, turn it into a mu, and pull the mu out. So let's do both of these. So here, working to the left, we get lambda f dot g, and then we pull lambda out and we get lambda times f dot g. Working to the right, this is equal to f dot l g, because again, this holds because L is self-adjoint. Now, LG, of course, equals mu g, so I can write this as f dot mu g, and now I can pull the mu out. This is mu times f dot g. I don't need to put a bar here because we already know by the first part that it's real. So now what we have is we have two different numbers, lambda and mu, and so f dot g, lambda times this thing equals mu times this thing, and lambda and mu being different means that that thing, f dot g, must be 0. If you prefer, I can say it like this. I can say this means that lambda dot mu times f dot g equals 0, and we know that lambda minus mu is non-zero, so we have a non-zero number times something is 0, and that tells us right away that f dot g equals 0. And that's what it means for the eigenfunctions, or eigenvectors, corresponding to distinct eigenvalues being orthogonal. So that's the end of the proof. In the previous lecture, we looked at what it meant for a matrix to represent a self-adjoint linear map between finite-dimensional, real, and complex vector spaces, namely Rn and Cn. And it meant that the matrix had to be symmetric or Hermitian, respectively. In this lecture, we're going to look at some examples and some non-examples of self-adjoint matrices where the vector space consists of functions and the linear operator consists of some sort of differential operator. Okay, so let's get started. We'll start with the simple non-example. So let L be the linear operator, which is the second derivative, d squared over dx squared. I'm going to write that for short as del squared x. I don't know if it's much shorter, but I guess it's a little bit more compact. So that's the linear operator, and consider the vector space C infinity on 0, 1. So that is this space of smooth, so infinitely differentiable functions on 0, 1. And I don't even need to specify whether the output is R or C. It doesn't matter. And all the derivatives have to be continuous. So I claim that this is not self-adjoint. And typically, if a linear operator is not self-adjoint, then it's not too hard to find a counterexample. Most functions are going to do. So what L does is L takes a function f and it outputs the second derivative. And now the inner product, I haven't actually told you what the inner product on the space is. There's a lot of ways we could define it. But let's just define it as f dot g equals the integral from 0 to 1 of f of x, g of x, dx. Now actually I haven't specified whether these are real valued or complex valued functions, so just in case they happen to be complex valued, I should probably put a bar there. But if we're sticking with the real valued functions, then the bar doesn't do anything. Okay, so depending on the context, if there's some sort of Fourier series or some other application, we might have to, or might want to put a constant out in front. I'm not going to do that here. It's not going to at all change whether or not a linear operator is self-adjoint or not. So make it simple and stick with this inner product. Okay, so let's take two simple functions. Let's take f of x to be x, because I know the second derivative of that is 0. And let's say that g of x equals x squared. Okay, so now LF is a function, LF is 0, and LG is equal, the second derivative is equal to 2. So let's compute LF dot G, that is the inner product of 0 and 2, which is the integral 0 to 1 of 0 times 2, so 0 dx equals 0. Is that equal to f dot LG? Well, what is f dot LG? F is x, LG is 2, so this is the integral from 0 to 1 of x times 2, so 2x dx, and that is certainly not equal to 0. So these things are not equal, so therefore this linear operator is not self-adjoint. We just did a non-example, so let's now do an affirmative example, and let's use the same linear operator. So L is the second derivative, d squared dx squared, which I'm going to write as d squared x. And even though this is not self-adjoint on the space C infinity of, well, I said 0, 1, but really any interval A and B it's not going to be self-adjoint on. So even though L is not self-adjoint on here, these are two subspaces for which it will be self-adjoint. So let's look at them. So the first one I'm going to say is C0 infinity of AB. So these are the smooth functions that vanish on the endpoints at A and B. So if I were to sketch something like this, suppose A and B is like here and here, then a function that would be in this space might look like this. And it doesn't have to be continuous. It could be piecewise continuous. Well, in general, it could be piecewise continuous, but I am specifically defining C to be the space of continuous functions. It's not hard to extend this to be piecewise if you want, but for now, it's so much easier to do it this way. The next space, this is called C perp infinity, or maybe C infinity perp, doesn't matter, on A and B. This is the space of all functions that are smooth, so that are continuous and are infinitely differentiable with continuous derivatives. And here we require that their derivatives are 0 at the endpoints. So now if we have, so here's what a function might look like here. So it just has to be flat at the endpoints. And this perp, think of this, so the reason for this notation is because in higher dimensions, maybe you have a region R, and what we want to specify is that maybe the F is like heat, and we want no flux to be through the boundary. So the boundary of this is just this boundary region, and suppose we want F to represent the heat, and we want no heat to pass through the boundary. That means that the directional derivative in normal or perpendicular to the boundary is going to be 0, and that's why this perp here it represents normal to the boundary. So in a one-dimensional region, normal, or the boundary is just 2 points, A and B, and we want the rate of change at those 2 points to be 0. Okay, so let's get started. Let's show why this linear operator is self-adjoint on these two spaces. And you may recall that functions or I should say these two boundary conditions, f of A and f of B being 0, are called Dirichlet, and these two boundary conditions are called Neumann, or type 1 or type 2 if you prefer. Okay, so let's see why this is true. Okay, so start with LF dot G. So I'm going to do the first one, but then it'll follow right away why the second one is true. So LF dot G. So this, oh, I also didn't tell you what the inner product is, so let's make things easier, and let's say that f and g is the integral from a to b of f of x, g of x dx. No surprise there. Let's just assume everything is real valued. I don't want to deal with complex conjugates. There might be a few technicalities. That's really making things harder than we need to. And there's nothing special or nothing tricky about showing this as self-adjoint. It's just basically integration by parts. So let's see it. Okay, so LF dot G, this is equal to the integral of a to b. So LF is the second derivative, so f double prime of x times g of x dx. So now we just have to integrate this by parts. So this is, I'm going to let u be equal to g, du to be equal to g prime dx, dv equals f double prime dx, and v equals f prime. Okay, so integrate by parts and we get u times v, so that's f prime of x, g of x, evaluated from x equals a to x equals b, then minus v du, or the integral from a to b, of v du. So that's f prime of x, g prime of x, dx. And now I'm just going to write this out a little bit. So let's see what I want to do. So I'm going to plug b into here, and I'm going to write that as, let's see, f prime of x times, not x, I'm sorry, x prime of b times g of b minus, let's see, so f prime of a times g of a, and then minus this integral, minus the integral from a to b of f prime g prime dx. Okay, let's compare that to f dot lg, which is the integral from a to b of f of x times g double prime of x. Okay, so we can do integration by parts again, or we could just, by symmetry, compare this answer to this one, is just reverse the roles of f and g. So if we do that, we get, let's see, we get f of x, g prime of x from a to b, and then we, by symmetry, well, f prime and g prime are here. We get the same thing, the integral from a to b of f prime of x, g prime of x dx. And now when we plug in a and b in here, so now we get f of b, g prime of b minus f of a, g prime of a, then minus the integral from a to b of f prime g prime. Okay, so what I want you to do now is compare these two things. I claim they are equal. So why is that? Well, both of them have this minus integral from a to b of f prime g prime. I forgot my dx here. Doesn't really matter. But now what about these two terms? Now I've color-coded it. So I want to highlight these boundary conditions in blue, the Neumann ones, and then these boundary conditions in red. So in this first space, so I'm actually going to show that this is self-adjoint, L is self-adjoint in both these spaces at once. Let's see if I can do that without having to erase things. Okay, so let's consider this first space. So now f and g have the property that f and g are both 0 at the endpoints. So let's look at this multicolored thing, f prime of b, g of b minus f prime of a, g of a. Well, in the first case, in these type 1 boundary conditions, then g of b is equal to 0 and g of a is equal to 0. So this whole term cancels out and we're left with just this integral of f prime g prime. And same down here. Down here, we have f of b is equal to 0 and f of a is equal to 0. Again, because f and g are 0 on this type 1 boundary condition, so I'm going to put this in orange. And so in both of these cases, these two terms fall out, and clearly LF.g and F.lg are just equal to this minus integral. So in that case, L is self-adjoint. Now for the second one, not much is different. It's just now that instead of g of b and g of a being equal to 0, so let me box this in purple. Now f prime of b is equal to 0 and f prime of a is 0. So both of these terms drop out, and similarly down here, g prime of b and g prime of a are equal to 0. Both of these drop out. So in both of these cases, these two terms drop out, and the inner product of LF and G is equal to the inner product of F and LG, and that's precisely what it means for L to be self-adjoint. Here's our next example. This is going to be more general than the two previous examples. So the linear operator, we're going to use the same one, L, the second derivative operator, but now we're going to look at the subspace. I'm going to call it C infinity sub alpha beta on AB. So alpha and beta, before I mention what the definition is, alpha is a vector, alpha 1, alpha 2, and beta is a vector, beta 1, beta 2. These are real numbers. And alpha and beta are non-zero vectors. They can have 0 entries, they just can't be all zeros. So a fancy way to say that, or compact way, I guess, is that alpha 1 squared plus alpha 2 squared is positive, and beta 1 squared plus beta 2 squared is positive. Okay, so this space consists of all smooth functions on AB, so infinitely differentiable with continuous derivatives. And here are the boundary conditions. So the left boundary condition at A is that alpha 1 f of a plus alpha 2 f prime of a is 0, and this right condition says that beta 1 f of b plus beta 2 f prime of b equals 0. Okay, so I said that the two previous examples were special cases of this. Notice that if alpha 1 and beta 1 are 1 and alpha 2 and beta 2 are 0, we get standard Dirichlet boundary conditions. So let me write that down. So Dirichlet, I'm not sure I'm spelling this right, I think that's correct, Dirichlet. This occurs when alpha, or type 1 if you prefer, alpha 1 and beta 1 are 1, and alpha 2 and beta 2 are 0. Neumann boundary conditions, or type 2, this occurs when the derivatives are 0. So this happens when alpha 1 and beta 1 are 0, and alpha 2 and beta 2 are 1. So alpha 1 and beta 1 are 0, and alpha 2 and beta 2 are 1. And we've actually seen another one. I think it was lecture 4.1. Whenever we talked about boundary value problems for the first time, we had an example at the end where the left boundary condition was Dirichlet, so alpha 1 was 1 and alpha 1 was 0, f of 0 was 0, and then the right endpoint was a mixed, so these are called mixed boundary conditions. It was something like, I think it was f of 0 plus, no, it was f of L plus f prime of L equals 0. That's where we got that tangent. So the solutions involved roots of x, it was the intersection of y equals negative x with a tangent function. So if you remember that, that was, I'm going to say previous example was when alpha 1, so that was the case when alpha 1 and beta 2 were all 1, so alpha 1 and beta 1 and beta 2 were 1, and alpha 2 were 0. But more generally, these things can be any real numbers as long as, again, both alphas aren't 0 and both betas aren't 0. So why is this linear operator on this general subspace self-adjoint? Okay, so let's check. So as before, we want to check that LF.G is equal to F.LG. Okay, so LF.G. I'm not going to go through all the details again because we just did it on the previous slide. But what I will say is that this is, let's see, so this is F prime of B times G of B minus F prime of A. I have to be careful with this. F prime of A times G of A, and then minus, we integrate from A to B, F prime of X, G prime of X dx. Okay, so now what? I'm going to go down here and I'm going to write what F dot LG is now. So this is the same thing, we just reversed the roles of F and G. So this is going to be F of B, G prime of B, minus F of A, G prime of A, minus the integral from A to B of F prime of X, G prime of X dx. Okay, so again, we did this on the previous slide. No difference here. So as before, these integrals are the same in both, so all we really have to do is show that this expression, these first two terms, equal these two terms. So how are we going to do that? So basically, here's the idea. I'm going to look at these two boundary conditions, and for each one of these guys is going to be, one of these alphas or betas is going to be non-zero. So let's suppose alpha 2 is non-zero. What I'm going to do is I'm going to solve for alpha prime of A, because I can move that to the other side and divide by alpha 2, because that's non-zero, and I'm going to replace the alpha prime of A here with that. Okay, so I'll show you what I mean. So there's going to be four cases. Let's first assume, so I'm going to write this on the top. Let's assume that alpha 2 is non-zero and beta 2 is non-zero, because we know one of the alphas and one of the betas is. So I'll do it in this case, and then I'll show you why it's analogous for the other three cases. Again, when alpha 1 and beta 1 are non-zero, or some sort of mixture. Okay, so if alpha 2 is non-zero, then we can solve for f prime of A. We can say that f prime of A equals negative alpha 1 over alpha 2 times f of A. And if beta 2 is non-zero, then we can solve for f prime of B and write this as negative b1 beta 1 over beta 2 times f of B. And now what we're going to do is see this f prime of A and f of B. We are going to substitute in for, here's that f prime of A, and the f prime of B is this. So let's do this. So this gets me negative beta 1 over beta 2 times f of B times g of B minus alpha 1 over alpha 2 f of A. Well, it's minus negative, so I'm going to put a plus there, and then minus this integral A to B f prime g prime dx. Okay, and now let's do that same thing down here. Now, do the same what thing. So these conditions hold for f, but also for g, because f and g are both in this space. So similarly, g prime of A is negative alpha 1 over alpha 2 times g of A. So I'm going to just replace g prime of B and g prime of A, just like what I did with f. The only difference is now there's going to be a g here instead of an f. So this is f of B times negative beta 1 over beta 2 times g of b, negative sign goes out there, minus f of a times negative alpha 1 over, oops, let me use red just to be consistent, negative alpha 1 over alpha 2, negative sign goes there, times g of a, and then again we subtract off this integral, f prime g prime dx. Okay, so notice that these two terms are the same as these two terms. This first one is a negative beta 1 over beta 2 f of b g of b, and this term is a negative beta 1 over beta 2 f of b g of b. This second term is alpha 1 over alpha 2 f of a, and look what I forgot. I forgot my g of a. Maybe you already noticed that. Sorry about that. And that term is the same as this down here, positive alpha 1 over alpha 2 f of a g of a. Okay, so what do we conclude? We conclude that these two things are both equal. Let me write that down. So these things are both equal, and this confirms that, or if these are equal for all f and all g, then L is self-adjoint. Now I made the assumption that alpha 2 and beta 2 were non-zero, and because alpha 2 were, so what I did is with alpha 2 being non-zero, I eliminated, or I solved for alpha prime of a, I could divide by that, and then I eliminated that down here in these two cases, f prime of a and g prime of a. And in the other one, because beta 2 was non-zero, I could solve for f prime of b, and I eliminated that. I eliminated f prime of b and g prime of b. But the same thing could have happened. Let's suppose that alpha 2 and beta 2 were 0, but alpha 1 and beta 1 were non-zero. If that were the case, then I could have solved for f of a and f of b. Actually, let me use a different color for the f of b. How about purple? And then down here, instead of replacing my primes, I could have replaced the values of the functions at a and v respectively. So for example, I would have replaced, instead of replacing f prime of b, I would have replaced g of b, and similarly I would have replaced f of b with a similar expression. It would have been negative beta 2 over beta 1 times f prime of b. So let's just say, I'll show you that. So if beta 1 is non-zero, then we can say that f of b equals negative beta 2 over beta 1 f prime of b. So then we could have eliminated the f of b's and the g of b's. And similarly, we could have eliminated, using this, we could have solved for f of a. So again, we could have said that f of a was equal to negative alpha 2 over alpha 1 f prime of a, and we could have subbed in, we could have eliminated g of a and f of a. So there's 4 cases to handle. I just did one of them. It should be easy to see why. Because one of the alphas is non-zero, one of the betas is non-zero, you can solve for that corresponding term and just eliminate this, and you get, in all 4 cases, that both of these terms are going to end up being equal, and therefore these two expressions are equal, and that's exactly what it means for L to be self-adjoint. The examples on the previous slides are one-dimensional examples. So the regions are these intervals a, b, and the boundary of these regions are just 2 distinct points, namely a and b. These things will arise when we study Sturm-Liouville theory in the next lecture, and then later on in the course when we study partial differential equations such as the heat or wave equation in one dimension. But a lot of this holds more generally. So now let R be a bounded region in n-dimensional space with a smooth boundary B. So I can't draw this in more than 3 dimensions, so imagine R, just here's a mental picture for you to have throughout. R is some solid region. This is R, the solid region, and then the boundary, B. So smooth just means that there's no corners. So B, sometimes we write this as the boundary of R. I know that looks like the derivative operator. It's the same symbol. In this setting, the Laplacian operator, which is sometimes written as a capital delta, I prefer to write it as del squared, and I'll explain why momentarily. However you want to write it, it's the sum of the second partial derivatives from 1 up to n. So here's two different ways to notate that. Again, this is a slightly more compact notation. This operator is self-adjoint, but now in what space? So in the space V of infinitely differentiable functions that vanish on B. So smooth functions, but they have to be 0 on the boundary. So let me go back to why I like to call this operator del squared. So if you recall from vector calculus, del is this curious vector of differential operators. So it's partial x1 all the way up to partial xn. So if you take the dot product with itself, so del dot del, which some people write just as del squared, because you're taking it, that's how you multiply a vector by itself, I guess, is the dot product. So think about what this is. This is just, so you multiply each entry by itself and you add them up. Well, what you get is you get del squared over, or partial squared over partial x1 squared all the way up to partial squared over partial xn squared. And that's exactly what Laplacian operator is. This is a differential operator. So if I take the Laplacian and I apply a function to it, say a multivariate function, then that gets sent to f(x1, x1) plus ... f(xn, xn). So the sum of the individual second partial derivatives. Okay, so that's what this operator is. Notice that if n is equal to 1, then a bounded region with smooth boundary, that's just going to be an interval or a collection of intervals. In that case, the Laplacian is just the standard second derivative operator. So think of this as an n-dimensional generalization of what we did 2 slides ago, where so we had a second derivative operator and we had a region, and the boundary conditions said that the functions vanished on the boundary. Now there's other tweaks you can do to this. You can look at the ones whose derivative is 0, directional derivative is 0, normal to the boundary, and you can do that as well. I'm just doing this to give you a flavor for what one higher dimensional analog is going to look like. Now, I'm not going to prove it, but I will tell you that it is straightforward. So the proof is just like what we did in one dimension. You basically write out the integral. Well, you got to define the inner product, and not surprisingly, you integrate over the region instead of the interval. But once you do that, you basically write out LF.g and F.lg, and you use integration by parts to reduce these things. Now, integration by parts generalizes to higher dimensions. You may or may not have seen this. If you have, I do not expect you to remember this. I certainly don't. I have to look it up every time. But recall from vector calculus, remember that collection of theorems that you probably learned at the end? There was Green's theorem, Stokes' theorem, and the divergence theorem. They're all very similar, and they all related integrals in a region to a smaller integral along the boundary. So for example, you could take a triple integral in a region, and you could turn that into a certain double integral along the boundary. And some special cases of that, from that you can derive things like integration by parts in higher dimensions. And everything works out the same. So basically you take these two things and you use integration by parts and the fact that these functions vanish on the boundary to get the terms to cancel out. So I encourage you, if you are curious, to look it up, but it really does follow by the same reasoning that the one-dimensional example does. I do want to say one more thing about the Laplacian. is a linear operator, and it has eigenfunctions or eigenvectors and eigenvalues. And the eigenfunctions, by definition, are solutions to the following PDE. So del squared f equals lambda f. So for example, if f is a function of two variables, x and y, then this PDE right here is fxx plus fyy equals lambda f, and this is something that we are going to need to solve when we study partial differential equations. This is called the Helmholtz equation. Another PDE that we really want to solve is called Laplace's equation, not surprisingly, and that's Laplacian of f equals 0. So in that case, this is f in two dimensions, is fxx. Well, it's two dimensions in Cartesian coordinates. It's different in polar and spherical, and so forth. But that's this PDE. So this is another PDE that we want to solve. We are going to need to solve both of these, and both of these will have physical interpretations. So we will see more when we study the heat and the wave equation in the next series of lectures. Let's conclude with an example from quantum mechanics, which is a big, important application area for everything we're doing in this class, in particular Fourier series, self-adjoint operators, boundary value problems, and PDEs. So the Hamiltonian is a self-adjoint operator written as h, and it's defined as follows. So it's negative h bar over 2m times Laplacian plus v. And here h bar is Planck's constant. It's this constant that you may have heard of. It's this tiny number that is inherent to the universe somehow. That's about all I'm going to say about it. It's h, and it's 6.626 times 10 to the negative 34, and I think the units are joule seconds. And then h bar comes up a lot too. Often you need to divide it by 2 pi, so that's h bar. It's just h divided by 2 pi. So that's what this operator is. V is a real potential field, so that's some function. And this describes the energy of a particle of mass m in a real potential field V. The eigenfunctions psi of h represent the stationary quantum states, and the eigenvalues describe the energy levels of these states. The eigenfunctions are solutions to the following PDE called Schoedinger equation, or the stationary Schoedinger equation. So the eigenfunction, by definition, these are the functions psi, such that when you hit it with h, you get back some scalar, capital E, of psi. Sometimes this is written lambda, like we do with the classical eigenvalues. So this is the eigenvalue, this is the eigenfunction, and they have physical interpretations in quantum mechanics. Okay, so why is this a self-adjoint operator? I think that's all I'm going to say about this. Is I'll convince you why this is self-adjoint. Well, we know that Laplacian is self-adjoint, and it's not hard to show that if you take a self-adjoint operator, or here's a better way to say it, it's not hard to show that the set of self-adjoint operators is a vector space. They are closed under addition and scalar multiplication. So if you add two self-adjoint operators, so if L1 and L2 are self-adjoint, then C1L1 plus C2L2 is self-adjoint as well. So we know the Laplacian is self-adjoint, and we know that is scalar times it is as well. And V, this is just a function, and I claim that this by itself would be a self-adjoint operator because it's what's called a multiplication operator. So in general, if L is a linear operator from, now I don't want to use V for my vector space, so let me use X for my vector space. If L is a linear operator, that just takes a function f and multiplies f by some function, say q, and then I claim L is self-adjoint. So this is self-adjoint. And the reason is, if you compute, LF dot G, so that's going to be, so I'm not telling you what the region is, so I'm just going to loosely say it's an integral, and either over region or with boundaries. So it's an integral of q times f, That's LF times G. I'll put dx, even though it might be higher dimensions. I think that's fine. And now I can rearrange things because these are just real valued functions. So I can certainly write f times q times g. And that is clearly just the inner product of f with LG. So anytime we have a linear operator that just multiplies a function by a fixed function, then that is self-adjoint. So now we have Laplacian, which is self-adjoint, and this multiplication operator is self-adjoint. And again, that's because, think about what h does here. H times a function, let's say omega, this is sometimes called a wave function. In other words, the input function. So h of this is negative h bar over 2m times Laplacian of omega plus v times omega. So v just tacks onto it. And again, this is self-adjoint because it's a linear combination of two self-adjoint operators. Okay, so that's a good place to stop. We are all ready for our next topic, which is Sturm-Liouville theory. Basically, we're going to take any second-order differential equation and look at the corresponding differential operator, and if we write it the right way, we can write it as a self-adjoint operator, and from that we can get an infinite set of eigenvalues and orthonormal eigenfunctions. So it's an amazing theory, and it really comes up when we study partial differential equations later on. So stay with us.